Our next presentation is from the University of Florida. The team name is UF Misterclín. The title of the project is Ultraviolet Technologies to Improve Cuba's Hospital Sanitation Infrastructure.
Whenever we're ready. Testing. Okay. We are Team Misterclín. My name is Julian. I'm a third-year biomedical engineering major.
I am Michael David Lopez. I'm a second-year mechanical engineering student.
My name is Matthew Espinosa. I am a second-year chemical engineering student.
My name is Nicholas Smith. I'm a first-year mechanical engineering student.
And we're presenting Ultraviolet Technologies to Improve Cuba's Hospital Sanitation Infrastructure. First, let's speak about the infrastructural context into which we're implementing our UV system. As we can see, much of the hospital infrastructure, at least that is available to the ordinary citizen, is in shambles. There are many airborne contaminants, and there's obviously inadequate sanitation of medical tools. We know this from ethnographic reports that adequate sterilization materials or equipment is often broken and unavailable. This situation is a breeding ground for nosocomial illnesses, which are illnesses that are acquired at the hospital setting. In this proposal, we're addressing both the airborne sanitation and the surface sanitation, using, on the one hand, an air purification system, and on the other hand, a UV cabinet. Now, what is ultraviolet germicidal irradiation? Well, UV light has ultraviolet properties. It's a little bit stronger than visible light, particularly UV light of 260 to 265 nanometers. Notice it causes irrevocable damage to DNA. Here, the germicidal effectiveness of UV light is between 260 and 265, and that coincides with the output of the majority of low-pressure UV bulbs. Now, does Cuba have the technological infrastructure to implement a UV bulb system? Well, we know they have fluorescent bulbs, and fluorescent bulbs are much like UV bulbs. The major difference, as can be seen here in this cross-section, is this phosphor coating. In fluorescent bulbs, this phosphor coating is responsible for converting UV light to visible light. Without that phosphor coating, it is essentially a UV bulb. The circuit also involves a ballast and a starter switch. The starter switch ionizes the gas within the bulb, and the ballast maintains proper current.
Okay, this is our design for the UV cabinet. The purpose of our UV cabinet is for surface disinfection. We used to disinfect small medical tools such as scalpels, scissors, and tweezers. And although UV cabinet technology already exists, we've constructed a model that is cost-effective and is made out of materials that are easily acquired, such as particle board, aluminum, and acrylic. As you can see here, the chassis of our model is made out of the particle board and is coated with aluminum on the inside. Aluminum is the most reflective metal with up to a 97% reflection rate, and this serves to contain the UV light within our cabinet and to ensure maximum exposure. Now, closing our cabinet is an acrylic door. The acrylic prevents the UV light from passing through, so that way the user is safe during operation. Now, over here is where the electronic components will be stored. This is a mechanical timer, and it plugs into any standard outlet. It goes from 0 to 60 minutes. And when set at 0, the light bulbs will be turned off. The only way the bulbs can be turned on is if the timer is set past 0. The wiring will then go from the timer to the two bulbs, which will be connected in parallel. It will then go to the starter and the ballast, which ionizes the gas so that the lights turn on. It will then go back into the other end of the bulbs, which then goes to a panel here on our door. Now, the door acts like a switch here in this circuit. So when the door is closed and the timer is set, the lights will turn on. But if for whatever reason the door opens, the circuit will open, and then the lights will turn off. This is implemented as a safety mechanism, so that way there's no direct exposure to the UV light. And we also included a lock and key here. We will now demonstrate the operation of the UV cabinet.
Okay, so I'm going to talk about operation of the UV cabinet, which is very simple. We're going to start off with the inspector, which hints us to our first step in the operation, which is the inspection of the UV cabinet. And what we're going to do is actually go inside the UV cabinet and inspect for any loose items, anything that's moving, anything that's doing what it shouldn't be doing. We're going to correct that, and after that, we're going to inspect the aluminum foil, which is a very key part of the disinfection process. It reflects the UV light and also protects you. So we want to make sure that there's no cuts, no holes in the aluminum foil, and if there is cuts, we want to actually replace the whole aluminum foil coating. We don't want to just like kind of rig it and put tape over it, because this won't help the disinfection process. It will be counterintuitive. So also an important part of the UV cabinet is that we have to keep this clean. Dust actually protects the bacteria and microbes in the UV cabinet, so this actually decreases the effectiveness of the ultraviolet light, as stated by this quote here. And like this dusting is very simple. We just want to dust it off, maybe wipe it with alcohol, and clean it before every disinfection process. Once we've done that, we can actually use the cabinet. Now, using the cabinet is very simple. When you're placing the items inside, you want to make sure you don't stack the items, because what stacking does is it creates shadows. And shadows will actually prevent the UV from hitting certain parts. An important thing before you put the items in is you should wash off like any material, like say you have blood on a scalpel, you want to wash that off before you put it in the UV cabinet. Now, once you've done that, you can close it, turn the timer on, UV will work. Now, also, you want to flip the items. You want to make sure you get both exposure to both sides just in case to ensure effectiveness. Finally, maintenance. Maintenance is very simple. All you have to do is replace the bulbs every 5,000 hours, which at maximum usage is about once a year. Additionally, just changing the aluminum foil. Very simple.
That was the surface disinfection portion of the proposal. Now we're discussing the airborne disinfection. For this section, we're using an ultraviolet upper room system. An ultraviolet upper room systems work by creating an irradiation zone of germicidal light near the top of the room. And as microbes flow through the room by natural convection currents, they are inactivated in the irradiation zone. Due to the ease of installation, the relatively cheap maintenance costs, and the few moving parts, it's very appropriate for a resource-limited country. Now, how does the light remain in the upper room? Well, this is accomplished by using a design first pioneered by Richard Riley. It involves louvers that direct light horizontally. We may create a small model to demonstrate this. See, in this case, the light passes through the louvers and is directed horizontally. This ensures the first fundamental principle of upper room design, and that is to maintain the level of irradiation in the bottom of the room to 0.2 microwatts per meter squared. Now, how are these fixtures organized in the room? Well, this has been determined mostly anecdotally, but a good rule of thumb with empirical evidence to back it is that 30 watts per every 200 feet squared is a safe number. We used, this is our model room to which our calculations are based off of, and that's the second fundamental principle. Now, there are two major variables that go into determining the performance of an upper room system. The first is the irradiance from a fixture. This is empirical radiation data acquired in the field. Notice how the majority of the irradiation remains within 30 centimeters vertical of the fixture. For our model, we use this 30 watt, we approximated with this 30 watt data, and we determined that there was 14.6 microwatts per centimeter squared in the upper room. This is relatively conservative. There are higher, more intense systems out in the United States. Now, the second major component is airflow. Now, airflow generally decreases the concentration of microbes in the air and is typically quantified by air changes per hour. Now, as this increases, the dose imparted by the UVGI system decreases because the microbes do not remain in the ultraviolet zone for very long. Now, as the flow in the room decreases, however, the ultraviolet system will compensate by eliminating more of the bacteria. Here we have, okay. So when it's shut, we see that the dose increases as it's shut. And here, the equivalent air changes is a measure of the effectiveness of the system, and that increases as the flow through the room decreases. Now, because the air quality improves with higher ventilation, the added benefit of our UVGI does decrease as the ventilation increases, but it's compensated by the fact that there is already larger ventilation, decreasing the concentration of microbes. Now, this is a measure of the whole of the system as a whole, as one unit, and we have, when it's fully open, that it increases the value. This is a general performance measure of the system as a whole, of the room as a whole. And these same principles can also be extrapolated to larger spaces, shared spaces where illnesses may be transferred.
Okay, now we're going to talk about the cost. How much does this project cost? Well, on the left, our chart represents the cost of the cabinet. We separate into categories of safety, lighting, and electrical. And the total cost is actually only $209.46 in US dollars. The same applies to the upper room system. We separated it by parts, and the sum of all that is only $116.36 in US dollars. Now, it's kind of hard to tell what an actual hospital how it might be structured in Cuba. So we based our model off of a book by Hirschfeld called Revolutions in Power 1959, and she described a hospital that had 500 rooms. So then we predicted if you have one upper room system per room, that's 500 upper room systems, and one cabinet for every 3 rooms, that totals to $93,648.30 to implement the entire project. Now, the operation and maintenance. The maintenance costs are actually very small. The only thing you really have to change is the UV bulb besides the occasional dusting, and that only sums to about $105 per year, and that figure is actually overestimated to account for any additional maintenance that might need to be done. Now, the operating cost. We developed this equation, and we did it based off a usage of 90% of the hours of the year. So if that's true, and we use the bracket that the energy consumption of this technology falls into, which according to Siegfried will only be about 0.09 Cuban pesos per kilowatt per hour per month, then the total operating cost will only be $6,834.41 in US dollars per year.
By implementing our system, we hope that the quality of Cuban healthcare facilities for the common people will rise to the standards of those of tourists and government officials. So that way the people get the healthcare that they need and then go to hospitals to get better, not to acquire new diseases. Thank you.